We normally wait like 5 minutes.
Yeah, sure.
We're not very punctual.
Nowhere.
Normally people make questions during the talk if
Yes,
you are okay with
that's
that.
perfect. Yes, yes, I prefer.
Moi, je viens d'installer dans l'appartement. D'ailleurs, je pourrais te donner, si tu as un appartement, c'est un calefacteur de gaz naturel. Gaz naturel. Et ça chauffe pas mal l'appartement, qui est petit par contre.
Ouais, d'accord.
Et c'est moins cher qu'électrique.
Mais justement, là,
Voilà.
on n'a pas encore d'appartement.
Bonjour.
Ça va?
Mais oui.
Quel miracle! Depuis
Où est-ce que c'est qu'on s'est vu? C'est à Paris?
On était copains
Ah.
au 2A
Ouais, ouais. Bah dis
à
donc.
Paris.
Ah,
tu,
bah.
tu m'as donné des coups de catamoton.
Ouais.
Tu m'as mené à la gare.
C'est vrai? I don't remember that. Ah, ok.
Et après, à l'X, tu as fait la thèse avec...
Avec Pella, oui. Ah, mais oui, ça y est, je commence. Mais oui, ça y est, c'est vrai. Oh là là, c'est le passé lointain. C'est le passé lointain. D'accord. Tu es ici maintenant alors?
Oui, je
Oui,
suis,
d'accord.
Oui.
Good.
Où est-ce que tu travailles? T'es à Paris?
Moi, je suis au laboratoire qui s'appelle APC,
Qu'est-ce
tu
que
vois,
c'est?
Astroparticules et Cosmologie. C'est nouveau, ça date il y a 10 ans à peu près, ça a été fait. Mais c'est très bien.
Ah oui?
Ouais, c'est bien, très bien.
Ah bon?
Voilà.
Et tu étais au CEA?
J'ai passé 35 ans au CEA quand même. Ouais. J'étais pas mal là-bas au service d'astrophysique. Mais j'ai arrêté
Catherine,
l'astrophysique. Oui, Catherine, qui était donc aussi m'a dit, parce que j'avais 2 directeurs de thèse, j'avais Catherine et aussi René. Et puis après, bon, j'ai continué au CEA, comme ça,
Ah bon?
pendant longtemps finalement. Et ici, tu travailles sur quoi?
Moi, je travaille sur les restes de supernovas, sur
D'accord.
les galaxies,
Ah,
sur la
ouais, ouais.
dynamique cinématique et dynamique
Des galaxies? Dans les galaxies?
Oui.
Ouais, d'accord. Ah, c'est bien. Ouais. Moi, j'ai fait un peu ça aussi, mais bon, j'ai fait beaucoup de choses. Mais j'ai arrêté l'astrophysique il y a peut-être 10 ans pour faire physique théorique.
Ah bon?
Et ça va être un peu physique théorique. Mais bien sûr, il y a des rapports toujours. Mais
Et tu
on
étais
va voir.
ici comment?
C'est l'ambassade qui m'a invité pour faire des conférences. Alors du coup, ben voilà, on a profité pour faire un séminaire ici. C'est très bien.
Et tu vas aller te promener?
J'ai pas beaucoup de temps. Je rentre dimanche.
Ah bon?
Et bon, je suis là à la semaine. Peut-être si tu veux, on peut aller boire un verre ou dîner ou un truc comme ça.
C'est-à-dire, je suis en train j'ai un postdoc
Ah oui.
et je vais faire un petit dîner très informel
Ah.
vendredi soir.
Alors,
Je sais pas si tu-
oui, je pense. Il faut que je vois avec les gens de l'ambassade s'ils n'ont rien prévu pour moi,
Et
mais
sinon,
je pense, oui.
on va vous faire
Sinon, ouais, d'accord.
jours.
Tu vas me donner ton
J'aimerais
mail et
bien,
puis on
oui,
va, ouais,
eh
oui,
oui.
comme ça on évoquera les vieux souvenirs. Non, mais vendredi, je crois c'est bien, oui, c'est.
Oui, et
ouais,
comme
on
ça
va-
tu connaîtras encore d'autres.
ouais, tu me donnes ton mail
Oui,
tout de
oui,
suite,
oui.
comme ça sera fait.
Oui, ça serait mieux.
Je vais le marquer tout de suite comme ça. Je vais t'envoyer un message. Bon, ça va pas partir tout de suite.
C'est avec des minuscules,
Oui.
tout. Marguerite.
Ah,
Marguerite, A-I-T, et comme ça.
hmm,
Ad, astro, point, unam, point, mx.
voilà.
Voilà.
Objet, contact. Dès que j'aurai une liaison, je te l'enverrai.
Bueno, el día de hoy es un placer tener a Marc Lachieze-Rey. I will switch to English because our guest speaks French, and I don't speak French. Right. So, Marc is a French astrophysicist, theoretist, and cosmologist from the CNRS. He works at the Astroparticle Cosmology Laboratory in Paris. Also teaches at the Central School in Paris. His research interests include topology of space-time, gravitation, and dark matter. He has also written many popular books in which he often recalls the cosmology principle, the heavy historical and philosophical heritage associated with it, as well as the current achievement challenges and perspective of this discipline. In his main research, he has these main questions. What are their physical significations and their different mathematical formalizations? How can we quantize them? This is about space-time and space-time. And cosmology and gravitation, he has the following research: geometrical models of the universe, topology of space-time, large-scale structure, determination of the cosmology parameters, dark matter, the Eros experiment, and the links with quantum physics. He has also several books, so if you want to see the bibliography, I have it here. We can check it later after his talk. Okay, so it's a pleasure. Go ahead.
Thank you very much. You hear me? You hear me? I hope you hear me.
The first row we can hear you.
Okay.
I don't know.
Okay. Okay. It's a pleasure to be here. And I used to be an astrophysicist, but now I am more theoretical physicist, and I will speak about theoretical physics. Of course, this has implication for astrophysics and cosmology, and I will try to present some of these implications. But my talk will mainly concern fundamental physics and even some mathematical points, because the search for quantum gravity is involving some very important and interesting and modern aspects of mathematics, and I will try to present them to you. I will try to be not too technical, but I think it's very nice and very interesting, this mathematics applied to physics. So I will try to speak about that in the second part of my presentation. So the question is, why search for quantum gravity? And there are different kind of motivations. And the first comes from quantum physics. And in fact, if you take quantum physics literally, it tells you that you can only study the evolution of an isolated system. And of course, strictly speaking, no system is isolated, because if you take, for instance, this room, it is in the gravity field of the Earth and the other planets. It receives some kind of radiation from the cosmos, different kind of radiations. So it is not, strictly speaking, isolated. And strictly speaking, the only isolated system is the universe. So in fact, quantum physics should speak only about one system, which is the whole universe. And this would be some kind of quantum cosmology. And if you do that, you have to consider wave function associated to the universe. And if you want to take the wave function of a small system like this room, or like an atom or an electron, this is just part of the wave function of the universe, but you have to know how evolves the wave function of the universe, how the universe evolves as a whole, and then you have to make some kind of quantum cosmology. And since the evolution of the universe is subject to gravitation, you have to include the gravitation in some way in that quantum cosmology. And so, in fact, this means that you have to do some quantum gravity. And maybe you know that there have been some trials to do quantum cosmology several years and several decades from now. And there is the very famous Wheeler-DeWitt equation, which is an equation concerning the wave function of the universe as a whole. And this is a very simple equation, but it has the originality that there is no time in it. and so it's difficult to interpret it. And also, it's an equation about the wave function of the universe. And as you know, in quantum physics, wave functions are related to probabilities. In fact, the square of the wave function, the square of the module of the wave function represents probability through the Born rule. But what means probability for the whole universe? Because when you have a quantum system and you calculate probabilities, you can interpret them as the probability that an observer observing the quantum system will find such or such results. But when you have the universe, the problem is that you have no external observer to the universe. So what is a measurement concerning the universe, and how can you assign a probability to such measurements? So there are a lot of conceptual problems linked to quantum cosmology and to Wheeler-DeWitt equation. And if you want to make quantum cosmology rigorously, I think you have to make first quantum gravity and to consider that quantum cosmology is a consequence of quantum gravity, like the classical cosmology, the Big Bang model, the Friedmann-Lemaitre models, is a consequence of the classical gravity theory, which is general relativity. So this is one first motivation, which is quite strong, I think. If you take quantum physics seriously, you must have quantum cosmology. So coming to astrophysics and cosmology, you know that there are problems in this field to be solved. First, we would be very pleased to have some information about the first moment of the universe story of near the Big Bang or near the Planck time. We would be also interested to have some insight about the physics of black holes. And you know that in these two situations, there is a conjunction of strong gravitational fields and very high density, pressure, temperature, which seem to require quantum gravity. So these two fields are a strong motivation to study quantum gravity. And also in astrophysics, we have the two problems of dark matter and dark energy, which are, of course, very different, but which both involve gravitation. And we don't know the solution of these problems. And one solution may be, for instance, the solution to the dark matter problem. You know that many people claim that the solution to the dark matter problem is not dark matter, but is a modification of gravity. So this is a possibility. And if gravity should be modified, if we have to change the general relativity theory to another theory, of course, which theory? And many people think that the correct theory of gravity, if it is not general relativity, should be a quantum gravity theory, or at the classical level, the classical approximation of a quantum gravity theory that we don't know for the moment, of course. And in fundamental physics, we would like to unify the interactions. If you look at the story of physics, of theoretical physics, it appears like a sequence of unification. For instance, Newton will unify the physics in the sky and on Earth. Maxwell had unified the electricity and magnetism and also light. Quantum physics is unifying matter and interactions, matter and radiations. So we have a lot of unifications. And you know that success, of course, in the 20th century was also the unification of electromagnetism and weak interactions to have the electroweak model, and also the standard model is not a true unification, but it's a global theory including also the strong interactions, but we have no coherent model including all interactions and gravity. So we would like to have such a thing, and since all interactions are quantized, it is natural to think that gravity should be quantized also. So the idea is to search for a quantum gravity of quantum theory of gravitation, to quantify gravitation. This is not the only option, because all people involved in quantum field theory know that quantum field theory is at best an effective theory, and that it is not the true fundamental theory. We don't know the true fundamental theory, and some people like Penrose and others claim that in that fundamental theory, gravity has a strong role to play, and so it should be some kind of maybe quantum gravity, or maybe it's a theory which has nothing to do with the actual formulation of quantum physics, which is something very different, which in some approximation would appear like quantum physics is described today, but it's very different conceptually. And one motivation for that is that, as you know, after 1 century, there is no satisfying interpretation of quantum physics, and people are still discuting about the meaning of measurement, what is the difference between quantum and classical system, and so on. So there are some insights in favor of the fact that fundamental theory is not the quantum physics as we have it now, but something which is fundamentally different. And in that case, the solution to this problem would not be to quantify gravity, but to find something different. But today I will speak about the possibility of quantizing gravitation.
So, sorry, this possibility could be, for example, string theory or superstring theory?
Well, it could be. Well, string theory, I think now it's no more very attractive. It has been very attractive many years ago, but yes, it could be something like that. And I will present some. Here you see that I mention some things which are twistors, non-commutative geometry. There are some new views on the world. There are some kind of new means to attack the problem of the fundamental physics. So these are some ideas. And you have also discrete approaches like network, causal sets. I will say some few words about that. And maybe this is something we have no idea at the moment. I don't know. Just some comments about the dark energy, because I think that this may be a motivation also for quantum gravity. You know, the problem is not directly what is dark energy, but the problem is that we observe that the expansion of the universe is accelerating if the analysis of data is correct, that I'll assume. And if we assume that this is not due to the average effect, I think the question is not solved at the moment. You know what is the average effect? Every people know, or maybe I explain, I don't know. No, I explain. Well, the idea is that when we interpret the cosmological data for any kind of, when we try to measure any kind of parameter, like the Hubble constant, or here the acceleration parameter, whose value is indicating that the expansion is accelerating. In fact, we analyze the thing in the frame of the Friedman models. But the Friedman models are cosmological models, are a solution of general relativity, which describe a perfectly homogeneous universe, spatially homogeneous universe. Of course, the real universe is not like that. And the point is that gravity, general relativity, is a nonlinear theory. And the point is that if you deduce a quantity from the data, if you deduce an average quantity from the data, the average quantity deduced from the data is not the same as the quantity deduced from the average data in some simple way. This means that it is true that if you want to know the exact value of, for instance, the acceleration parameter, you have to make some non-linear treatment, and this is, of course, completely impossible. So when you estimate that by using the homogeneous cosmological models, you make an error. And the question is this error completely negligible, as it was more or less implicitly assumed in all this analysis, or is it important? And if it is important, is it sufficiently important to mimic an acceleration of the expansion which doesn't exist in reality? And now we have no answer to this question. There are small groups in the world working on this subject, and I think really there is no firm conclusion about that. So there is a possibility that there is absolutely no acceleration of the expansion of the universe, and that this is only due to a misinterpretation of the data. But I exclude this hypothesis for the moment. And also you know that there is a perfectly correct explanation for the acceleration of the expansion, which is the cosmological constant. And if you have a cosmological constant in the theory of relativity, like it was introduced by Einstein in 1917, then you explain perfectly all the data with the precision, with the present precision of the data. And when the precision of the data is increasing, for instance, when we measure the parameter which express the second derivative of the variation of the density, then when the errors are getting lower, it's still in accordance with lambda. So there are, in my sense, strong arguments in favor of the cosmological constant explaining acceleration. But if you don't accept the cosmological constant, as many people do presently, this means that you should have a substance which is responsible for the acceleration of the expansion. So this means a substance which has a repulsive gravitational effect. In other words, a negative pressure. And of course, in classical physics, there is no such things. So the people claiming for such a dark energy are claiming that this is due to the influence of a quantum field. The problem is that we don't know presently what could be the gravitational effect of a quantum field. We don't even have no quantum field theory in curved spacetime, because the usual quantum field theory is expressed in Minkowski spacetime and is based on the fact that there is a well-defined time and that there are very well-defined symmetries, I mean the Lorentz symmetries. And in an arbitrary curved spacetime, I mean in presence of gravitation, of course there is no time, and most cosmological models have no time-like killing vectors, which is a condition to define some function which has the properties of time, and of course no Lorentz symmetries, because if you have galaxies, galaxy clusters, superclusters, filaments, this means that the universe is not completely Lorentz symmetric. And also we have no idea how a quantum field could gravitate. If you make the naive calculation in the present theory, you prove that the density energy of any quantum field is completely infinite, which is ridiculous. It has no meaning. So it could not be that. And then many particle physicists are saying that, okay, why the density energy is infinite? Because it's the result of integral going from zero scale to infinity. And it suffices to replace the zero in the integral by some cutoff. And then you get a finite density energy. This is true, but this would not be a quantum field theory. Why a cutoff? You have to justify that, and which value for the cutoff. And the problem, as you know, is that if you take some correct value for the cutoff taken from particle physics, which could be the Planck time or the Planck length or the length characteristic of symmetry breaking. Then you have an estimation for the density energy, which is 10 to the 120 orders of magnitudes wrong with respect to observations. And this is very strangely, this is called a cosmological constant problem. But if you assume that acceleration is due to the cosmological constant, precisely, you don't have this problem. So it should be named dark energy problem. And then if you have solved these questions, it remains to say what is the field whose energy is responsible to acceleration. Is that a field named quintessence? And you know there are hundreds of proposals for such things. But the point is that today the data exactly fit the prediction of cosmological constant. So if you have a field, it remains to explain how is it possible that the density energy of that field exactly mimic at a high precision the prediction of a cosmological constant. This would be a very strange coincidence. But anyway, the point is that if you want to solve these questions, we really need to know how a quantum field gravitates. So we need to know the relation which is between gravitation and quantum field theory and quantum physics. And probably this relation involves also a quantification of gravitation. So this is an additional motivation for searching a quantum gravity theory. So there is strong motivation to search for quantum gravity. And there is another motivation, which is that it is really fun. So I think this is the more important. And how to quantify gravitation. And there are, of course, many ideas. And no one of these ideas is really a theory today. No one has completely succeeded. There are partial results. And I will concentrate today on this approach. But first, I would mention what are called the covariant approaches. And this is not a very good appellation because precisely they are not covariant, but I will explain what this means. You have also the string brain theories, which are very complicated, and now it seems that there is no possibility to make prediction from them. So for the moment, they are not they seem not to be very interesting. And there is one point that this covariant approach and the string brain theories do not exactly quantify gravitation, but quantify the perturbation of gravitations, and this would give the graviton. But the point is that general relativity, which is a classical theory of gravitation, is a nonlinear theory. So I'm not sure it is very interesting to quantify the linear part of the gravitation, which is exactly what would be the graviton. And you have a theory of quantum graviton, but this is of no use because in the situations where you have strong gravitational fields, this linear theory is not interesting. And these are precisely the situations like black holes or the Big Bang or maybe the very small scale structure of space-time. All these interesting situations involve probably strong gravitational fields. So these approaches are not relevant. So the simple idea, in fact, is to quantify general relativity directly. And in fact, it appears that these covariant approaches, they were studied many decades ago, maybe half a century ago. And it appeared that it was a strong problem. They are not renormalizable. And if you know quantum field theory, there is a strong law which says that quantum field theory should be renormalizable. So it appeared that this was not renormalizable, and so many people during long time said it is impossible to quantify gravitation, and there have been during a long time no trials to quantify general relativity. But in fact, this was wrong, because if you quantify general relativity, as I will say, you quantify the geometry of space-time, because the message of general relativity, the big message, is that gravitation is the geometry of space-time. The gravitational field is the curvature tensor of the space-time. And if you quantify space-time, this means that you are not making a theory in a given space-time, which is a manifold admitting points. And since you don't necessarily have points, this means that you don't have necessarily these integrals going to zero. And what was shown is that, in fact, you can have a theory which doesn't need to be renormalizable to be a good theory. And this was realized, and this motivated the fact that you can search a quantization of general relativity, even if the perturbative theory is not renormalizable. In fact, to say it in other words, is that you will make a quantization which is not perturbative. And you know, if you know field theory, there are perturbative field theories, but the theory of quantum gravity should not be perturbative. And this is the case of loop quantum gravity. I will present you in a moment. As I said, there are other ideas and twistor, non-commutative geometries. They are not quantization of the gravitation, but they may replace, they may help to obtain a theory which has the same qualities that quantization of gravitation, and there are interesting options. They are quite technical mathematically, because twistor theory is nothing very difficult. This was invented by Penrose, but this is interesting use of spinners. In fact, a twistor is a spinner, not of the Lorentz group like the usual spinner that intervene in physics, but of a larger group which is called a conformal group. So a twistor is exactly what is exactly to the conformal group what the usual spinner is to the Lorentz group. Non-commutative geometry, maybe you know about that. The mathematical developments of this theory are due mainly to Alain Kohn, and there are many applications in physics, and some people are trying to develop a theory of a non-commutative space-time with non-commutative field theory and things like that. This is quite technical and quite special, but maybe this will bring some interesting results. And there are also some discrete approaches, because when we make classical physics, we assume that the frame for physics is space-time, which is something continuous. And mathematically, this is described by a manifold, and a manifold is a generalization of the notion of space, which is assumed to be continuous. This is a topological space which is continuous, and to have also some differentiability properties, and this is called a differential manifold. And this is very interesting, because in the differential manifold you can formulate equations and you can solve them. And in physics we like very much to have some equations, and we like very much to solve them. But if they are differential equations, we must know what means differential, what means derivatives, and for that we should use the frame of differential geometry and of manifolds. But manifolds are, in fact, continuous objects. And if you remember what I said before, many problems are due to the continuity properties of manifolds. Because when this famous integral goes to zero, it goes to zero because we have points which are infinitely close to each other. So these problems come from the continuity of the space-time. But when we observe space-time, we never observe a continuous space-time, because we observe particles here and here and here, electrons, protons, neutrons. They are very close together, but they are not completely at zero interval. So in fact, what we observe is discrete. One proton, one neutron, very close, but at separate positions. And secondly, it appears that when we make, for instance, loop quantum gravity, there is naturally a discrete character of spacetime which emerges. So there is an idea that, in fact, many problems of our physics are due to the fact that we make physics in a continuous framework, which is spacetime. And if we replace this continuous spacetime by something which is discrete, maybe we will have more success. And there are many attempts of such things. And a last remark, which is mainly mathematical, but is about a new mathematical theory, which is called category theory, which is some kind of generalization of set theory. This is mathematics, but this mathematics show a very strong adaptation to physics. It seems to have a very natural character of being adapted to physics. And I will say a few words about them because I like them very much. It's very interesting, and they apply to all this subject. I think this is a part of a recent mathematics which is really helpful and probably mandatory to make a new physics.
Marc, can I ask you something very naive? In relativity, you have manifolds, which describe the concentration of matter in different places, right? And these are discrete. I mean, one manifold is not the same as another one. So by construction, it's already discrete.
No, because matter is inside the manifold.
Right.
But the manifold is a continuous, it's like space. For instance, space is the space in which we live, the Newtonian or Euclidean space, is a manifold. It's continuous because it has a lot of points. It is true that the points where you have particles are discrete, but they are discrete elements of matter in the continuous manifolds. Because if you have a proton and a neutron in a nucleus which are very close, between them, even if they are very close, there are an infinity of points. Because if you take a very small part of the real line, between any points, you have an infinity of points. And this is exactly what continuity says. And when you integrate, for instance, the equation in quantum field theory, you have these equations which go to zero, from zero to something else. And this is why they diverge, and this is why you have all these infinities and singularities. So a manifold, by definition, because a manifold is a continuous topological space. It is continuous explicitly, and a differential manifolds is not only continuous, but it is also differentiable, which is something more. And what is general relativity? The problem. I will go to my transparency because I have that somewhere. Oops. Sorry, no. Okay. The problem of general relativity is that you have a differential manifold, and you want to find a metric G on that differential manifold. And the metric, mathematically, if you have a differential manifold with a metric, this is becoming a spacetime. This is becoming what is called a Lorentzian manifold. A Lorentzian manifold is a differential manifold plus a metric. So you have a space, you have a set, you have continuity, so the set becomes cosmological. You have differentiability, so the space is not only topological but also differentiable. And then you have a metric, and it becomes a Lorentzian manifold, and it becomes a spacetime. So the metric is what transforms the differential manifold to a Lorentzian manifold or a spacetime. And the metric physically represents gravitation. And the problem of general relativity is given some limiting conditions, maybe at infinity, and given a source of gravity which is expressed by a matter energy momentum tensor, you want to know what is the metric. And this is given by the Einstein equations, which tells you that the Einstein tensor corresponding to the metric, to this metric, is proportional to the matter energy tensor plus a gravitational plus a cosmological constant. The Einstein tensor, this term is more or less the second derivative of the metric. And this is a reminding of the equation of Newtonian physics. You know that in Newtonian physics, you have the Poisson equation. The Poisson equation tells you that the second derivative, which is called the Laplacian, of the gravitational field, delta phi, is equal to the density multiplied by the Newton constant. Here, this is the same. The second derivative of the gravitational field, this is the metric. The second derivative, this is the Einstein tensor, is equal to the generalization of the density, which is the energy momentum tensor, multiplied by that. This is just the Newton constant divided by 8 pi. Okay, so this is a tensor generalization of the Newtonian physics, but the metric represents the shape of space-time. But at the beginning, you have a differential manifold. And so if you consider general relativity as a field theory, this means that this field theory is expressed on a manifold. And you have to find the value of the field, which is the value of G. And if you want to consider all possible value of the fields, this is the space of all metrics on the manifold. And this is called Lor de M, because this is a space of all Lorentzian metrics that you can have on a given manifold. And the problem of general relativity is to find what is the point is that space which describes the real universe. So finding the good metric is finding the good point is in that set. And if you want to go from a classical field theory to a quantum field theory, you will have to construct a quantum theory on that space, more or less, which is, in some sense, the state space, because each metric is a state of the gravitational fields, or a configuration of the gravitational field. So, in fact, this is the space of the possible states of the universe. And in fact, well, this is rather technical, but if you take two metrics, we have some kind of relation between them. In fact, they correspond to the same physical solution. So in that space, you have different points which represent the same physical solutions. So when you look at the physical solutions, you have to count these different points. This equivalent class of points has only one solution. So the true space of configuration, the true space of physical space, is not exactly that set, but that set quotiented by the equivalence relation. And when one says that two diffeomorphic metrics correspond to the same physical solution, this is exactly what is called covariance. Everybody has heard that general relativity is a covariant theory, and to say that is to say that two metrics, two shapes of space-time which are related by a diffeomorphism represent the same physical solution, represent the same gravitational field. So this is the classical theory of gravitation. What is interesting, so the field for that is Riemannian or pseudo-Riemanian geometry. The difference of Riemannian and pseudo-Riemanian geometry is that in Riemannian geometry, the metric is always positive. In Lorentzian geometry, it can be positive or negative. And so the geometry of space-time is Lorentzian just because you have not only space, but you have time and space. And when you take the metric length of a small vector or a small piece of curve in space-time. If this square is positive, this means that this is a time-like vector. If it is negative, this is a space-like vector. And if it is 0, this is a light-like vector. So the vectors of the curve with a null metric length represent the light. And the fact that the length of a vector is 0 is the traduction in the language of geometric relativity that the velocity of the light is constant equal to c. And when you have a differential manifold with you have connections which live on that. Do you know what are connections mathematically, or who knows exactly what is a connection? No. So, okay. This is a very precise mathematical notion which was invented in the beginning of the 20th century, and which is the basic expression for gauge theories. But this is also the basic expression for general relativity. When you have a manifold M, and you recall that if you want to make general relativity, you have to start from a manifold M. Manifold, I repeat, has not a lot of structure. It is simply continuous and differentiable, and nothing more. But it admits many connections. Connections are something which allow to derivate the vectors. Because when you have a differential manifolds, to say that this has a differential structure means that you know how to make derivation of function. When you have a differential manifold, you know how to make derivation of functions, so you know how to write and to solve differential equations. But it is impossible to make the derivation of a vector. And in physics, you would like to make derivation of vectors. And this is exactly defined by a connection. So when you have a manifold, you can define many connections on that manifold. And this connection have some properties. They have a curvature. They have other kind of properties. And a connection, in fact, it has nothing to do with the metric a priori. You have your manifold M. You can define connection. You can define the metric, and this has nothing to do. But you can ask something. You can ask that the connection transport the metric by not modifying it. Transport the metric parallelly, one says. And if you ask that, you realize that there is only one solution. So when you have a metric, this defines a unique connection which is called the Levi-Civita connection, which plays a very important role in relativity. For instance, when you want to define what is a geodesic, and this is very important in general relativity, what is a geodesic, because geodesic is exactly the path in space-time which is followed by a free particle. If you want to explain what is the orbit of the Earth around the Sun, the answer is that the Earth is following a geodesic in the space-time curved by the Sun. The Moon is following a geodesic in the space-time curved by the gravity of the Earth. So the notion of geodesic is very important, but the notion of geodesics is linked to connection. When you have a connection, the connection transports a vector, and if you ask that the vector is transported parallelly without changing, this means that you have a geodesic. So, in fact, many notions which are linked to the metric are in fact defined from the connection implicitly. The notion of curvature is in fact the curvature of the connection. The geodesics are in fact the geodesics of the connection, but usually one says this is the curvature of the metric, this is the geodesics of the metric. So this notion of connection is very important too. I will not spend time on tetrads and cotetrads because this is very important too, but I will explain that in that way. When you formulate general relativity, this is a field theory. And in a field theory, like in any dynamical theory of anything, you have dynamical variables. For instance, if you want to study the dynamic of a particle, the variable is the position of the particle, which is changing with time. If you want to study general relativity in the usual formulation, the dynamical variable is the metric. And then you express the dynamics of general relativity by a Lagrangian, which is called the Einstein-Hilbert Lagrangian. And this Lagrangian is exactly the integral over space-time of the element of integration. This factor, which is the determinant of the metric, and this is the curvature of the metric. And this is very well known. And if you take this Lagrangian, this action, in fact, this is not the Lagrangian, this is the action. The Lagrangian is that part. And if you say that you apply the Euler-Lagrange principle, and you say that the solution is the value of the variable which makes the action stationary. So you ask that when you vary the metric, this doesn't change. This is the Euler-Lagrange equations. And when you ask that this is stationary, you obtain the Euler-Lagrange equation for the metric, and this is exactly the Einstein equation of general relativity. So Einstein equations are derived from this Lagrangian, and this was shown by Einstein himself in the beginning of the 20th century. But you have another way to express general relativity, which is to say that you have two different variables. You have a metric, G, and a connection. And then you write the Lagrangian as the same thing, but saying that this is a function of the metric, and this is not a function, this is not the curvature of the metric, but the curvature of the connection. And then, since you have two different dynamical variables, you will assume stationarity of the action with respect to both variables. And when we assume that the action is stationary versus the connection, you obtain that the connection should be the Levi-Civita connection linked to the metric. And when you vary with versus J, you obtain Einstein equations. So this formulation, known as the Palatini or first order formulation, is equivalent to Einstein-Hilbert equation. Not completely, but almost. And you have a third formulation, which is very interesting for us, which is called Cartan-Dirac formulation, which means that you replace the metric G by something which is related, which is called a cotetrad. And cotetrad is just a technical word for orthonormal frame. You know what is, when you have a manifold, you know what is a frame. For instance, if you have a plane, which is a two-dimensional manifold, a surface, you can have two basis vectors at each point, and this is a frame. When you have a four-dimensional manifold like space-time, a frame is just four basis vectors, because you have four dimensions, at each point. And if you have that frame is orthonormal versus the metric, with respect to the metric, this is an orthonormal frame, and this is called a tetrad. So this is a different formulation of the general relativity theory, and this is interesting because this is only this one that people have been able to quantize, to begin to quantize. So you have two different variables, which are the tetrad or the cotetrad, which is written A, and the connection, and this big omega is the curvature of the connection, which is written with a small omega. So I don't want to be too technical at this point. Now you want to quantize general relativity. And the problem, I have 10 minutes. Okay, I will go very quickly. The problem is that the most important quality, I would say, of general relativity is that time doesn't exist. So you have no time. But when you look at the usual way to quantize a theory, it makes use of time. So you cannot quantize general relativity like usual theories. And the additional problem is that you don't even have a metric, because the metric is just the result of the problem you are asking. So at the beginning, the metric is the result. You don't have metric at the beginning. So you cannot apply usual rules to quantize gravity. So how will you do? You will introduce artificially something which is an ersatz of time. So instead of using space-time, you will cut your space-time in slices. Space-time has 4 dimensions. So you will cut space-time in slices which are each has 3 dimensions. And in some sense, this is space. And the dimension of the slicing is time. You call it time and you call that space, but this is not time or space because this is made completely arbitrary. This is something, you have many ways to do that, to split space-time into space and time. And this is called RDM formalist because of the names of the guys who invented that. So now you have chosen a time function. This is completely arbitrary, I insist. And then you have time and space. And instead of saying you have a space-time, you say that you have a space which is evolving with time. This is a different conception of the same things. So you have a space sigma involving with time. And instead of saying you have a space-time metric, you have a spatial metric, which is a 3-dimensional metric evolving with time, plus something additional, which are called lapse and shift and so on. Well, so this is not important, but now you have something which is exactly like time, and what you will do, you will quantize exactly like if this were really time. Of course, this is not, and at the end, you should restore the fact that this is arbitrary. Technically, you should restore the covariance, because when you do that, you are breaking the covariance of the theory, and the covariance is a fundamental theory. So at the end, you should recover the covariance. And this happened naturally because you have something which is called constraints. And I will try to finish here because I have no time to speak a lot of more. But the point is that you succeed to quantize the theory in this way, using a formulation which was invented by HTK, and there are very interesting innovation in that theory. You succeed to quantize that theory, which means that you have an Hilbert space of states, like in usual quantum physics, and you have operators acting on the states, which represent all the measurements you can do on that. So you have some kind of quantum geometry. But the point is that you should have this constraint. And when you do classical, non-quantum general relativity, you know how to solve this constraint. And from that approach, where you have splitted space-time into space and time, you will recover the covariant approach when you have a space-time. But the problem is that in the quantum counterpart of that, you don't know how to solve the constraint. And this is where the theory breaks. Because, in fact, you have some kind of quantum theory of the geometry of space, and this works very well, but you don't know how this theory evolves. So you don't have a dynamical theory. You have, in some sense, a kinematical theory. You know the geometry of space, but you are unable to know how it evolves. And I want to say 2 points about this geometry. First, since it is quantized, you have some wave functions. There are wave functions of space of entire space. And these are very strange mathematical beings which are called spin networks. And the fact is that there's wave functions, and they are really wave functions in the usual sense. They are described by very strange geometrical beings, spin networks, which are in fact some graphs, which some indices on each edge of the graph, spin networks. And this is the quantum aspect of the geometry of space. And if you want the geometry of space-time, we have to know how the spin networks evolve. We don't know, but we have a name for that. They are called spin foams. So if we manage someday to really find the dynamical aspect of loop quantum gravity, because this is loop quantum gravity, probably the solution would be spin foams. But now we only know spin networks, which are the geometry of space. And the second thing I want to say is that, like in all quantum theory, we have operators. And if you have a usual quantum system, you know that the system is in a given state. And if we make an observation of that mathematically, this means that we apply a quantum operator on that state. Here, this is the same. Since we are in geometry, we have quantum operators. We have quantum operators of surface. We have quantum operators of volume. And the very interesting fact is that these quantum operators cannot give any value. They give quantized value. And for instance, they don't give the value 0. This means that if you measure a surface or a volume, you can only obtain some definite values, which are more or less multiples of the Planck length. So a surface cannot have any value. It should be some kind of multiple of Planck lengths that you can calculate from the theory. And in particular, it cannot be 0. And this is very interesting because if you make cosmology, the Big Bang, the idea of Big Bangs comes from the fact that the volume of the universe goes to 0. But here, this is not possible because the operator tells you that there is a minimum value, which is a Planck volume, the cube of the Planck length, more or less, with a factor. So in the past, when the size of the universe was getting smaller and smaller, there is a limiting value, which is a Planck volume. So you cannot have Big Bang in the cosmology from the loop quantum gravity. And so you have maybe a bounce, a quantum bounce on that. And you have many applications of this theory. So I will stop here because time is flowing. But I hope I have given you a taste of how you can obtain this loop quantum gravity theory. And of course, there are many possible applications in the field of astrophysics and cosmology, also concerning black holes, because maybe you know that the application of this loop quantum gravity to black holes already has given the good formula for the entropy of the black holes as it was calculated in 1974 by Bekenstein, and this is considered the main success of the theory. Thank you.
Questions?
Comments?
Well, I want to welcome Marc Lachieze-Rey because we have made studies of the EA of Astrophysics at Meudon, and I welcome him to be in Mexico and to change your studies to astroparticle and so on, and to try to solve those interesting problems of the dark energy and dark matter that are some puzzles that we have now in science. And I think that this kind of approach, of new approach in order to understand science is quite interesting.
Oh, yes.
Welcome here.
Thank you. Well, it is very interesting, and I enjoy doing that anyway. I'm not sure it will bring the real solution to all our problems, but it's really enjoyable.
What are the two constraints that you were talking about?
The two constraints, they express the covariance. One is called the Hamiltonian constraint or the scalar constraint, and it expresses the fact that you can choose any time function. And it expresses what is called also the time reparametrization freedom. This means that if you have chosen a function, a time function, you can choose any other time function. For instance, you can choose, you have called the first function t, you can choose a second function, which is, I don't know, exponential of t squared. This is another one. And if you use this one or the second one, this gives exactly the same result. But when you make the calculation, it doesn't give the same result. And the constraint expresses the fact that you should, in fact, have the same result. And this appears as a constraint that the solution should verify. And so this is for the first constraint. The second one constraint is the same thing, but not for time, for space. Because when you split your space-time into space slice, so you have to choose a time function, which goes vertically, if you want, and you have also to choose a shape for the slice. And exactly like for time, the result should not depend on the way you have chosen for the shapes of your slice.
So the constraints, one is space-like and the other
Yes.
one is time-like.
Exactly. And so since it's time-like and there is only one dimension of time, in fact this is a scalar, and it is called sometimes also the scalar constraints, and the second one is called the vector constraint or the diffeomorphism constraint or the spatial constraint, depends. And in fact, for some reason you have a third constraint, but this is more complicated.
Yeah, but how do you choose those constraints?
You don't choose them, they appear naturally. And in fact, if you make forget general relativity, forget quantum physics, you make just dynamics, usual dynamics, Lagrange dynamics. I don't know if you know the Lagrange dynamics. Lagrange dynamics is just to say that when you have, for instance, a particle that you call this position Q, and you want to know the dynamics of the particle. You have a Lagrangian, which depends of Q and the derivative of Q. And this is a Lagrangian formulation. And when you want to quantize, you go to Hamiltonian formulation. And from the Lagrangian formulation to the Hamiltonian one, you have something which is called a Legendre transform. And this Legendre transform, in some case, can be singular. If it is singular, this means that there are some symmetries in the Lagrangian. And if the Legendre transform is singular, this means that when you look at the theory from the Hamiltonian point of view, you will have constraints. This is a result of the fact that the Legendre transform is singular, which is itself the result of the symmetries of the Lagrangian. So if you have symmetries in the Lagrangian, gauge symmetries, then you have constraints automatically. You find them by the calculations. And this famous time representation invariance is a symmetry of the Lagrangian, because this means that if in the Lagrangian you replace t, the time, between quotes, by any function of time, you get the same result. So this is a symmetry. This will appear as a constraint, and exactly the same thing for the other one. So you don't have to assume the constraint. They appear exactly, and they are some kind of motion equations. And in fact, what you call in relativistic physics, what you call the motion equation is exactly the same that the Hamiltonian constraint, which is called also the scalar constraint. And you can say that in other words, the Hamiltonian is the generator of the time transformation. This is true in usual dynamics, this is true in quantum physics, and this is true in general relativity. This is a very, very strong statement valid in world physics.
Okay. Well, I guess it's time to finish. But we have some snacks, and we can continue discussing about this more informally. But let's go to have some snacks. But thanks to the speaker again.
We'll see you tomorrow. Sure. Okay. Bye now.